السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Inshallah we will probably, I'm not very sure, but probably we'll finish inshallah the practical issues session today, or we'll take maybe part of the next lecture inshallah. Today we'll focus first on a very important concept in machine learning called cross-validation. Okay, what is that and why we need it? Remember the training and test split that we have to split the labeled data that we have into training set and test set, right? Right? Why do we need to do that? So that we can test the model, right? We need to test the model on unseen data. So we split our data to training, so we can train a model and then test on unseen data. Type. What could be the disadvantage of this? Is there any problem with this setup? What if when I do this split, we usually do it randomly, right? What happens if all the positive examples came to be in the training set, or all of them came to be in the test set? That might happen randomly, right? Right? Of course, this is the extreme case, but generally, the representation of or the distribution of the data of the training set might not be as the test set. Okay, so in that case, whatever we are testing on is not representative enough. Okay, so that's one problem. Another thing is that when we do that, we are actually testing on one part of the data, right? So we are not using the entire data that we have. We are using the large portion of it for training, but for test, we are testing only on small set. Okay, and testing on small set might not be reliable, right? We would love to test on much larger data so that we can get a performance that will reflect the actual performance of the model in the future, on more realistic or more unseen data. So we have two problems here. The random split might not give us a representative set, and we are testing on only part of the available data. We are using most of the data for training and just a small portion for test. Okay? Right. What is the solution for that? The solution for that is a concept called cross-validation. What is cross-validation? We will test the data not only on train and test, so two splits, one split, but we'll have k folds. We will divide the data into k folds, k parts, k portions. Okay? Usually k is 5 or 10. Let's say k is 10. So we will divide the data into 10 folds, 10 parts. As you see here, this is the, let me change this. This is the entire data. Okay, maybe better to use the, okay, so this is the entire training set, right? So we divide it into 10 folds. We'll take k minus 1, or in this case 9 folds for training, and 1 for test. That's exactly like what we did before, right? That's not new. We usually do that, right? We take big part for training and small part for test, right? But the new thing here is that we will do that 10 times. Every time we will change the test fold. So, in the first iteration, if we look at the first iteration here, we have this fold to be the test set. So we will train the model on these 9 folds and then test it on this fold. For now, we'll assume that we don't have hyperparameters. Okay, we'll deal with the hyperparameters in maybe the next slide. Okay, but for now, let's assume that we don't have any hyperparameters. Okay, so we only need training and test sets. So the train set will be the 9 folds, and this one will be the test fold. In the second iteration, we'll change the test fold. It will be that fold. So now we are testing on this and training on which ones? These folds. Okay? Every time we change the test set, we train a model from scratch on the new training set, and test on the test set and get an evaluation measure. So for the first one, we'll get an evaluation measure. How? We trained on already the model on this first 9 faults, and then we test on this fault. We compute the evaluation measure, let's say F1 or accuracy. So we get a number here, an evaluation measure here, and then we get another one from the second iteration. Then the third iteration will change again the test fault, and that of course means that we'll change the training faults. So we'll train a third model and test it on this test set. We get a third evaluation measure, or evaluation number, an estimate of the performance, and we do that 10 times. Every time we change the test fault and train on all the others. So that's the idea. Instead of doing it once only, so the first iteration is actually what we usually do, or what we used to do before, right? Just one split. Train and test. With cross-validation, we repeat that k times. Every time, or every iteration, we use a different test set. Okay? Do you understand first what we are doing here? Any question about how this works? Right. Why we are doing it that way? What's the benefit? Are we here actually testing on the entire data set, or again testing on just one test set as before? Just one? One every iteration, right? But overall, after we are doing all of that, it is like testing on the entire data. And remember that from each iteration we get an evaluation estimate, right? After the 10 or the k faults, we average them to get the average performance of the model. Actually here we trained k models, not just one model, right? So we get the average performance of them to be a representative performance estimate for the model. Yes?
In the first iteration, and then the next one, in the first 8 faults, the model has already seen them. So why do we?
Okay, good question. Notice one thing. In every iteration, we train from scratch. We don't continue training. So this model is trained on, and for iteration 1, is trained on faults from 1 to 9, right? In the second iteration, we train from scratch a new model on faults 1 to 8 plus 10, and test only on 9, and so on. Exactly, that's my next question. Are we breaking the major rule of not touching the test set? No. In every iteration, we train on some faults and we test on completely unseen faults to that model. And in every iteration, we have a new model. Okay? Yes. That's another good question. Now we have 10 models, right? Which one we should actually use in reality, right? After we do this training and after we get a measure here, which one we should use? That's a very good question, and there is no gold answer to it. Okay? The best answer, or one possible answer, is to use the model that has the best performance among these 10. Okay?
But it's based on what, small or large numbers?
Based on?
Like, how do I know which one is the best performance?
Based on the meaning of the measure here, right? All of them, whether accuracy or F1 or precision or recall, they favor the high number means better, right?
So wait, so they're returning the precision recall these stuff or just a number? What are they returning?
Precision and recall are numbers also, right? What do you mean? So let's say that the evaluation measure is F1. Okay, so I will compute F1 for this iteration. I will compute F1 for that model, and for that model, and for that model, and then average.
I was asking if it's fixed F1 for all time.
The evaluation measure itself,
Yes.
of course, it's fixed. Otherwise, there's no meaning of that. Yes. 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 Usually we use we set k to 5 or 10. That's the standard. 5 folds or 10 folds. Yes.
Why we're taking the average of the
What do you want to take? Because we want a measure at the end that will tell us overall what is the performance of the model. Yes, now that's why we want the average performance of them to be a reliable or more reliable estimate of the performance. Okay? Yes.
Can we train each iteration on the same model?
We train the same model? What do you mean by train the same model? You mean the learning algorithm?
Here in each iteration, we are changing the parameters of the model.
No, we're not changing the parameters. We are training a new model. Okay. Let's say that we are training perceptron. Okay. So for the first iteration, we will use for training these folds only from 1 to 9. We get a model. Okay. So let's call it M1 because it's first iteration. Okay. In the second iteration, we'll train a model on from 1 to 8 and then and 10. Okay, so different training set. So we'll call it M2 and so on. So every iteration we are creating a new model, a different model, because the training set is different. And we also test on a different test set. Did I answer your question?
So we are
We are changing
changing
that. Yes, we are. I don't want to say shuffling because shuffling is completely random. Here we did the random splits once and then we use the same folds. So we are, in every iteration, we are changing the training and test sets.
but not the model.
When you say model, you mean the trained model or the learning algorithm? The trained model, of course, we are training from scratch with every iteration. Of course, when we train the model from scratch, the parameters, the values of the parameters of the model will change. That's why it's a different model. So the model that we will get here, let's say, for example, the perceptron. What are the parameters of perceptron? The weights and bias, right? So here you will get weight 1 and bias 1. Here you will get weight 2 and bias 2. Different. Might be different. Might be the same, but generally they are different. Of course, that's why we say it's a new model, because the training set is changed. Okay? Okay?
Doctor, I have a question.
Yes.
So here, for example, if E1 is picked, do we take this E1?
You mean M1, not M1, the model.
Yeah.
Yes.
So this model's train and test ratio is picked.
Sorry? Say it again.
So if a model is selected, we take that model's training and test ratio, or this is
For what?
different?
For what? For reporting the performance?
Yes.
No, for reporting the performance, you report the average performance over all of them. Okay. Type. Any other questions on this? I said earlier that we assume that we don't have hyperparameters, right? Type. What if we have hyperparameters?
Okay.
What should we do?
We have fold for the
Yes. One solution is that in this iteration, you see we have how many training folds? 9, right? We can split this 9 into maybe 1 fold as a div and 8 as training, and do the same thing that we did before. Okay, so that's one solution. That's one solution. Do you understand this? Type. Another solution is within these 9. Let's say that we are within this iteration. Okay, we have 9 for training and 1 for test. Okay. Another solution is within these 9, we do cross validation, inner cross validation. Okay, but now the folds will be train and div. Okay, so in the previous solution, we said take 1 fold as div, right? Why should I take, for example, this one? Why? Maybe I can take this. Maybe I can take this, right? Maybe I can take this. Which one? I can do it randomly, take one, or more properly done, you can do it using cross-validation. You can try this multiple times as we did in the previous slide, but now for tuning the hyperparameters. So let's focus on this now. Let's see that we are in iteration number 1. Okay, where we have a test fault, which is, if you remember from the previous slide, it was number 10, right? And the train was 9 faults from 1 to 9. Right? Now I will take this whole training set and divide it into 5 folds. So now I have 5 folds. 1, 2, 3, 4, 5. In every iteration now, I will consider one fold to be a div set and the others to be training. Exactly. No, actually, you can change k in outer and the inner, but yes, if k is the same, then it will be k-square iterations. Yes. Okay. So within each iteration from the previous slide, we can have this. But I want to make sure that you understand one point here. First, you understand the concept here, that within one iteration, we can do this again. It will be like two nested loops. The outer one, the previous slide, the inner one, this slide. Okay? But the purpose of these two are different. The purpose of these two iterations or two loops are different. In the previous slide, the purpose was to get a better estimate of the performance. We changed the test set. Okay? So instead of just estimating the performance on one fold, no, I will estimate the performance on the entire data set by changing the test set. Okay? Now, what is the purpose for this one? Tune the hyperparameter. Exactly. Okay, so tune the hyperparameter so that we get the best possible performance for every iteration. Okay? Is that clear? So the goal is different. The outer cross-validation is to get a better estimate of the performance. The inner one is to get better model by tuning the hyperparameter. Okay? You will see that this algorithm in the book, this algorithm in the book is for the inner cross-validation. So this is for tuning the hyperparameters. Okay, if you want to do the whole thing, then you put this inside another loop for testing. One thing that I want to say about this algorithm quickly, because it was misleading. In the algorithm, it says train and test folds. But actually, because this is a hyperparameter, I would change this test to be div, just not to be confusing. Okay, but this actually test is the div set. Okay, the one that is used for hyperparameter tuning. Right. Any questions so far? Is the concept of cross-validation clear? It's, just to be honest with you, it's one of the challenging concepts to understand. Okay, and usually it is really confusing. So I want to make sure that you understand it. Yes?
I know that the performance is going to be measured with the average.
Performance will be?
It's going to be measured eventually with the average, 1 over 10, and the sum of the all.
The performance, yes.
Yeah, okay, but then we are going to pick one model.
Yes.
Which has one specific E. So why the average is an indication for the one?
Okay. Okay, the answer is that I understand your point, that you are saying, okay, we are taking one of these models, but the performance, we take the average. If you want to avoid that, then you can retrain on the entire data. Okay, when you retrain on the entire data, the estimate will be more close to the actual performance of that model, instead of just training on 9 folds or k-1 folds of the data. Okay. Did you get this point? So in reality, يعني after we do this, let's get back to the to this slide. After we do this, let's say that we don't have cross validation, or we do the tuning on just one fault, the first solution. Which model we will use in reality? After we do this, we get an estimate. Let's say that the average performance was F1 equals 0.45. Okay? Type. Which model that we should use? Two ways. There are two ways. One is to get the model, is to use the model that got the best performance, or retrain the entire model. Again, retrain a new model on the entire data, not just on 9 faults. You can, right? Nothing will prevent you from doing that. Fine. Any other questions? Now we can take this to the extreme. What is the extreme? Is to have the number of faults to be the number of training examples. Yeah, let's say that I have 100 examples. I will set K to 100. What does that mean? For training, in every iteration, I will train on 999 and test on one example only. One example only. This is called leave one out. That's the extreme. Okay, that's the extreme. This is called leave one out. When K is N capital here is the number of training examples. Type. Why would we do that? That's too much, right? Yani we will have the number of iterations in this case will be what? Will be N, which is the number of examples. Why would we do that? No, training on most of the data doesn't mean that it's overfitting. And it's actually we would love to train on as much as we can. Okay? But why would we do this extreme? Yes. It's not? Why is that? But we will repeat that. Remember, there are iterations. There are iterations. Still, it's not the case that we will just test on one example. Actually, we'll also test on the entire data, but one at a time. We'll build a model in every iteration. The reason why we should or we would do that is when the data set is really limited, it's really small. So we want to train on as much data as possible. Okay? So training the label data that we have is very limited, very small. So if I divide it into 10 folds, I'm always training on 90%. Okay? I want to train on as much as we can and then test on the least we can, which is one example. But of course, this will be on the entire test set eventually. So we use that when the data set is very small. Okay? Is that clear why now? Yes or no? Yes. Type. Any disadvantage of this? Any drawback? What's the problem with that? Yes, it's a lot of time. Even if when the data set is relatively small, it's not very small, it will take time, of course. It will take time. Okay, cross validation in general, of course, takes more time than just one split, right? Just than the standard way that we did before, which is one split. Just have one training set, one diff set, and one test set. Of course, doing that will have more time, and even more when we do leave one out. That's the extreme case. Okay, so we should not do that when we have large data. It will need a lot of time and power, of course. If you have the power, computing power, and you don't care about time, then of course you can do that. This will give us a good estimate of performance because you are training on the most possible size of the data. Any questions about cross validation? The last point before we leave. We said that it is expensive, right, in terms of time. But if you really think about KNN in particular as a special case, it is natural. It's very straightforward. Why is that? It won't take much time actually for KNN in particular. Why?
Because it's already calculating all the distance.
Type. What is the problem again with the one out? Now we are building so many models, right? In training, right? يعني every iteration we build that we build a new model and test on just one example, right? We build, يعني if we have 100 examples, how many models we will build? We will train 100 models, right? طيب, in KNN, what do we do in training?
Not training.
Huh?
Not training.
No training, nothing. Okay, so it will be just testing. It will be just testing. So it's very natural for KNN. That's a very special case. Okay, so you can use that even with a bit larger data set, but that's also only because the training is trivial for KNN. Yes.
So isn't one of the drawbacks is that we're taking the evaluation on one example only?
But we are averaging on all examples at the end. That's the fix of it. When you average over all, it's like averaging over the entire data set.
Because at the end we're taking one model.
In all cases, at the end, we will use one model only. In all cases, so that's not different.
One model with only validation, like validation of one example.
Oh no, you can train. No. Good point. Good point. In this case, it's better just to train on the entire data set. That's usually what we do at the end. And at the end, after you get the values of the hyperparameters, you just train on the entire data training set. Okay. Good question. Any other questions? Cross validation is good or bad?
أكتر واحدة ممكن نستخدم cross validation عشان نشوف البرفورمانس تبع مثلا decision tree بعدين نشوف k means أو كده يعني بحيث إنه ده estimate.
Okay. Cross validation, we mentioned that we do it in two ways, right? One, to get a better performance evaluation, and the other one is to get better model by tuning the hyperparameter in a better way. So use it the way that you like. طيب, we'll stop that inshallah here.